Good morning to everyone. We are going to start our morning sessions. We have three speakers before coffee break. So the first of them is Cullan, who is going to talk about cosmology and cosmography with galaxy peculiar velocity surveys.
Good morning, everyone. I have the privilege of being your first talk this morning. So my name's Cullan. I'm a postdoc from the University of Queensland. And the aim of my talk today is basically to try and convince you that this sentence is true, which is that combined redshift and peculiar velocity surveys allow for some of the most precise cosmological tests of gravity in the low redshift universe. And so the way I'm going to try and do this is first tell you what are peculiar velocity surveys, for those of you who are unfamiliar with them, how they can be combined with redshift surveys, and how we use them for cosmology and cosmography as well. I'll show you some of the current constraints that we've got and some of the things we're working on currently, and also what we expect in the future. Okay, so peculiar velocities. So these peculiar velocities of galaxies are basically the motions of galaxies in departure from the Hubble expansion, and they're effectively sourced by gravity. Okay, so galaxies move due to the expansion of the universe and due to gravity. And as the peculiar velocities are sourced by gravity, they provide a direct link to different gravitational theories on large scales. Hopefully this equation is not new to any of you. This is just the equation for redshifts. And so typically when we observe a redshift, we have this thing on the left-hand side. There's a component here, which is the cosmological redshift due to the expansion of the universe. And then there's this term in here, which is the peculiar velocity due to the gravitational forces felt on the observed galaxies. And this is a map, for instance, of the gravitational forces in our local universe. And the reason why these velocities are useful is basically you can get directly from this equation of motion here from linear theory, which basically says that the velocity of a galaxy on the left-hand side is related to the density near the galaxy on the right-hand side by this parameter here, in fact, by both these parameters, but in particular this parameter here, which we call the growth rate of structure. And this has strong predictions from general relativity. In particular, many of you will have seen this expansion before, where you basically say that you can approximate the growth rate as omega matter to some power of gamma. And in GR in particular, the growth rate of structure only depends on the amount of matter in the universe, with gamma of approximately 0.55. And it also importantly doesn't change with scale, so it's scale independent. And so in particular, if we were to ever detect a scale dependence in the growth rate of structure, this could be seen as a smoking gun for general relativity. And so the way we often measure the growth rate of structure is using a technique called redshift space distortions. If any of you at the school last week, you will have hopefully learned some about this as well. And these are very common to use because redshifts are very, very easy to measure over a large cosmological volume. However, as I'll show, the information actually saturates in the local universe due to a phenomenon we call cosmic variance, which is basically saying that no matter how many galaxies we observe at low redshift, there's only a finite number of modes we can measure in a certain volume, and so adding more galaxies does not improve our precision on the constraints. The way redshift space distortions work is basically we have galaxy redshifts from which we infer some positions. We expect that the cosmological redshifts should be isotropic, but what we see is that the peculiar velocities effectively act as a contaminant in that and cause this distortion in the apparent relative locations of galaxies, which on large scales is this squashing when you go from real to redshift space, which is the famously called Kaiser effect. And on the nonlinear scales, the non-sort of linear motions cause a smearing along the line of sight, which is equally famously called the fingers of God effect. But one alternative actually to measuring the impact of velocities is to actually try and measure these velocities directly. So rather than treating them as a contaminant, which you then have to model in the observed positions, you can measure them directly. And this is tricky. People have been trying it for, I guess, over 40 years now, but large samples of this are finally becoming available. So how does this work? So turning back to this familiar equation, what we effectively have is we have a redshift that we can measure from the spectrum of a galaxy. We have a cosmological redshift, which we may be able to get from a distance indicator. And if you can measure both of these separately, you can get the peculiar velocity in the middle. And so what you really need is you need a distance indicator from which you can infer the cosmological redshift. A famous example of a distance indicator is type 1a supernovae. You can use type 1a supernovae to do this. And people have used type 1a supernovae to compute the peculiar velocity of the host galaxy. But the two main distance indicators that I'm going to talk about today are the Tully-Fisher relationship, which is a relationship between the rotation speed and the absolute magnitude of spiral galaxies. And basically, if you can measure the rotation speeds, typically from H1 surveys, although not necessarily, you can infer its absolute magnitude, and the peculiar velocity effectively adds scatter in the vertical axis here. And so you can compare the apparent magnitude and the absolute magnitude, and you can get a distance. You can also use something called the fundamental plane relationship, which is a bit more complicated because it's three-dimensional. But for elliptical galaxies, you can measure the radius, the effective radius of the galaxy, the surface brightness, and its velocity dispersion. And you can then infer what the true size of that galaxy should be from the fundamental plane. And you can compare it to its apparent size on the sky. And again, that comparison between true and observed size tells you an angular diameter distance. And so it works as a distance indicator. And so on that front, we recently released a new survey of fundamental plane galaxies, or a new catalog rather. So this is called the Sloan Digital Sky Survey Peculiar Velocity Catalog or survey. Apologies for the double survey there. Can't help it nowadays. So this was released last year, and so this is the first to include some redshifts up to 0.1. So we now have peculiar velocities which go quite far in the local universe. Compared to previous data sets, the SDSS data is shown in the blue here at the top. It's mainly in the North Galactic Cap, but is much denser in sampling and far more galaxies than in previous surveys. And now, with all these sort of data sets combined, we now have quite a large number of peculiar velocity measurements that extend all the way out to redshift 0.1, particularly with this new SDSS catalog, which extends up to higher redshifts, and with samples like the Cosmic Flows 4 Tully-Fisher sample and 60F, which fill in the lower redshift stuff where the distances are more accurate. And so this is really kind of an unprecedented amount of data. Each one of these data sets at the time has become basically the biggest data set of its kind. And so we've transitioned from a time where we had a few thousands of these measurements to a time where we now have about 55,000 of these measurements. And so this, in particular, this sample alone is twice as many galaxies as all previous surveys were combined. So before SDSS, we had 17,000, and now we've added another 30. So I'm going to tell you a little bit about how we actually did this. And so one of the things we had to do was basically come up with new methods to fit the fundamental plane of galaxies. So the fundamental plane is shown here again. So this is exactly what we're modeling and fitting to get our distances. On the y-axis, we have a measurement of the rotation of the radius, of the galaxy. And this is effectively telling you its size. And on the x-axis, we have the velocity dispersion and the surface brightness. And by calibrating this relationship, you can effectively predict the size a galaxy should have. You compare it to its observed size. And so any offset from the best fit line here tells you the peculiar velocity. It's basically a comparison between its predicted size, which is a straight line, and its observed size, which is somewhere offset from that. The typical uncertainties on these actual measurement parameters are tiny. That's shown here. So really the dominant source of uncertainty here is intrinsic scatter in this relationship. We're attributing that all to the peculiar velocities, but the fact is there's many astrophysical processes which contribute to that scatter, and we don't understand them all. So that's what gives you the errors on your peculiar velocities. But one of the things we also were able to do with this data set for one of the first times is produce a very large ensemble of realistic simulations that we use to test this. And the reason we had to do this is because as you go to high redshift with these surveys, it's very important that you have very good control of your systematic errors. And in particular, a very small difference here in this eta parameter, which is effectively the distance to the galaxy, as you go to high redshift, can translate through into a very large velocity. So the velocities of galaxies we're trying to measure on the order of a few hundred kilometers per second. If you have a slight tilt in this line as a function of redshift, that means you're getting a net velocity across your entire sample of a few hundred kilometers per second. So that means your systematic error is of the same size as the signal you're trying to detect. And so with mocks and careful calibration, we're able to basically confirm that our pipeline is unbiased, and we'll give unbiased fits and mocks. One interesting finding of this peculiar velocity survey was that there was a bias that still remained after we did all this careful calibration. And this is effectively a correlation between the distance of a galaxy we measure and its group richness. So that's completely unexpected. We don't expect that galaxies in richer groups should be have basically larger values of this. It should all be constant or scattered about the zero line. And we actually tied this back to the fact that the velocity, the surface brightness, the mean surface brightness, tends to drift in different samples with different group sizes. And so we corrected for this, as shown in this plot, basically by fitting different subsamples of this data with separate fundamental plane parameters. So those parameters are those shown here. And when we do that, we recover the blue binned points, which is effectively a more unbiased estimate of the distances. But the actual cause of this is still unclear. And so if anyone has any ideas, please come and talk to me. In particular, what we're finding is that the group richness is correlated with the mean surface brightness. We don't know if that's physical. For instance, it could be that different galaxies, different groups have different assembly histories, and so they have intrinsically, physically different surface brightnesses. It could be systematics in the sense that maybe it's difficult to measure the surface brightness of an elliptical galaxy when it's in a very dense environment and get very accurate measurements. But anyway, so once we have these pure velocities, that was a quick taster of how we get them. What do we do with them? Okay, so this is where the cosmology comes in. And so one of the key things to remember about when you measure pure velocities directly is that those pure velocities are sourced by gravity, and that gravity itself is influenced by all matter in the universe. It's not just the baryons, it's the dark matter as well. And so what that means is that if you've got measurements of pure velocities, those measurements are effectively bias-free. There's no galaxy bias terms entering, at least on linear scales in these measurements. This makes it a very powerful probe of the growth rate of structure, compared to, for instance, redshift space distortions, where galaxy bias and the growth rate enter in a completely degenerate way. And so, for instance, you can see this if I make a measurement of a power spectrum from those velocities. That's exactly what's shown here. This is if I take those pure velocities and I measure a power spectrum in the same way I would for a bunch of redshifts. And you look at the shape of this and you look at what it looks like from linear theory, you find that in linear theory, these two components of the power spectrum effectively can be modeled like this. And the term at the front here is directly proportional to the growth rate squared. There's no galaxy bias in here. And almost just by fitting the amplitude of this curve, you can get a constraint on the growth rate. So that's why they're very powerful. And even more usefully, the velocities and the positions at low redshift can actually be combined. And if you do the maths, you find that if you combine and jointly fit both of them, you actually overcome this cosmic variance limit. That means that while the information in the local universe saturates, if you've only got redshifts, if you have redshifts and pure velocities, because you're measuring the same density field, but with two different traces, you're effectively overcoming that cosmic variance. And so there's no saturation of information, and you can always do better if you have enough galaxies than you would with only redshifts. And so we've also been developing some methods to model this. And so the way this works is we model the likelihood of those fields directly. So what we do is we take a bunch of redshifts, and from there we say we basically have a density field. We take a bunch of pure velocities, and we say we have a velocity field. You can get both of those on grids for the local universe, and then you can model the likelihood of observing those. You can do it in a very clever way. For instance, Sapranta, if you have any questions, can answer one of the clever ways of doing that, using reconstruction and actually reconstructing the local universe. Or you can just fit a simple Gaussian likelihood and get constraints on F sigma 8, which is what we've done here. And this is work that's been primarily led by my student, Jan, who has a paper on this that came out earlier this year. So these are the two data sets we actually fit. What we've done is here we've taken some redshifts and we've computed the overdensity in a grid, effectively. We've also taken this, what we call log distance ratio, which is effectively a pure velocity. If you times this log distance ratio by light times c times the redshift, you get a velocity. And you have that as well on the grids. And where the cosmology enters is if you model the covariance between all of these fields. So what you do is you can write down the likelihood. This is a simple Gaussian likelihood. This is your data vector, which is just your gridded positions and velocities. And this covariance is where all the cosmology enters. So you vary the covariance matrix, and you vary the likelihood, and you can fit for cosmology. This covariance matrix actually has 4 terms. It's got basically the correlations between 2 points in the density grid, correlation between 2 points in the velocity grid, and the correlations between a point in the density grid and a point in the velocity grid. Okay? And so you could do this with just redshift space distortions, in which case you'd only have the CGG term. You can do it with just the velocities. You only have the covariance and the velocities. But if you do all 4, you find that you can get better constraints. And in particular, you can overcome the cosmic variance limit. Actually evaluating these is an absolute nightmare. This is one example. This is pretty scary. But fundamentally, it's just integrals over the power spectrum times some sine and cosine functions. And more importantly, all the sort of usual suspects are embedded in these expressions. In particular, you have some cosmology that enters into these terms here. You've got the growth rates. You've got some correlation functions, effectively. These are just correlation functions in the same way that you can measure and model the correlation function. You've got some galaxy bias, which enters because you've got the galaxy density fields. You've got some nonlinear redshift space distortions. So it takes a long time to compute this, but we came up with some clever ways to do this quickly. And then you can also add in things like shot noise in the density field. You can add in pure velocity errors, so measurement errors. you can add in the fact that you've gridded your data. And the punchline is that if you do this and you minimize the likelihoods on our new data, you find constraints that are consistent with general relativity. So here I'm showing that same procedure applied to all the some of the mocks that we produced. For each of the mocks, you can produce a growth rate measurement with some uncertainty. The reduced chi-squareds of all of these fits is generally quite good, which means that our procedure is modeling the fields pretty well. And most importantly, we find that you get a constraint on the growth rate, in particular, which is shown in this column here, which is consistent with GR, which is the dashed line. So the predictions of GR match the constraints on the growth rate that we find. So this is quite a good confirmation of the growth rate structure. And that's not new. I mean, other people have also demonstrated that as well. And all these other parameters are simply things like galaxy bias and nonlinear redshift space distortion. However, if you really want to read into this, you might find that this constraint on the growth rate tend to prefer a slightly lower value of F sigma rates. This is actually something that pure velocity surveys have been telling us for a while. And so, in fact, most constraints that you find on F sigma rate from pure velocities tend to be on the low side. And so this is something that we're going to continue to investigate in the future. Most of the measurements you find down here, so this is basically all below redshift 0.1, generally come from pure velocity surveys. And so these constraints, if you take them individually, don't seem to point to much, but as an ensemble, they seem to point that gravity may be slightly different than GR would predict. So that's one thing we can do with pure velocities. We can look at their clustering, and we can measure things like the growth rate of structure. Something else we can do is we can look at things like the average velocity in our patch of the universe. And we also find something interesting there as well, which is, again, not new, and people have been finding this for 20 years. But more importantly, the new data we've got, which is an order of magnitude more data than we previously had, does not resolve this, and in fact makes the tensions worse. And so one of these tensions is that if we measure the average velocity of our local universe, we find that that velocity is higher than you might expect from a lambda CDM prediction. Lambda CDM plus GR, I should say. Here's an example of that measurement. So here is basically the amplitude of the velocity of the data. So when you just take all the velocities in your survey, you average them, and you calculate the average velocity, you find something on the order of 400 kilometers per second. This is true if you take all of that data I showed earlier, which is 55,000 data points. It's also true if you split into the individual subsamples. The error bars get larger. There's still always a tendency to have a larger than expected bulk flow. And this is true also regardless of the depth of the measurement that you're predicting. So as you go to larger and larger volumes, you'd expect that the average velocity would tend to zero over time due to homogeneity and isotropy, but we're finding that it doesn't. And in fact, these points here and this gray error bar are the measurements using exactly the same technique we've used in this data on lambda CDM mocks. So you can see that the lambda CDM mocks both decay as a function of distance, as you'd expect, and are on the order of 200 plus or minus 70 kilometers per second. But the data that we fit with the same technique has a very large bulk flow. And so this is basically a reconfirmation of stuff that people have been finding for a long time with smaller data sets. And we found that this actually persists even if you change the estimator you use entirely to calculate this measurement, all of which those estimators are found to be unbiased when we apply them to our mocks. This was also pointed out in another paper earlier this year, which we effectively confirmed the results of to some extent. And more importantly, we've also had a detailed look at whether or not systematics can affect this. And the punchline is that if there's a global systematic affecting all our data, for instance, we got H0 wrong, that would not explain this. Okay, so these constraints here are immune to changing the overall amplitude of the velocity, so the overall amplitude of H0. What we can't rule out is that there's calibration issues between these data sets that is causing some of this. But as you can see from this plot, they would need to be very large. Basically, these calibration issues between individual data sets would have to be so large that it's quite surprising we haven't seen them. And in particular, this is the data that we're actually fitting. And one interesting thing is that if you look at this bulk flow, you find that it kind of points in the directions of two relatively well-known objects. It's kind of halfway between Shapley, which is this kind of faint blue point here, very difficult to see, but it's over here, and somewhere over here, Shapley, and also the Vela supercluster, which is hidden behind the, which is a supercluster we expect to be there, but it's hidden behind the galactic plane. And so really to resolve this, what we need is more data in the southern hemisphere, which is where a lot of this data is missing down here, and also potentially in the galactic plane, which is very difficult to get. But as I'll say in a minute, some of those data sets we have in the future could resolve this. Something else we can use curiosity surveys for are just to look at the reconstructions. So here's an example of a reconstruction of our local universe, a nice map that you can produce that was produced by Sopranta. Here's another one more recently where you can see the impact of the new data which goes out here, and in particular you can see this line here, which is the Sloan Great Wall. This is basically the velocity lines falling into the Sloan Great Wall. And other things you can do are things like measure the power spectrum to get the growth rate of structure. Earlier I was showing this fields method. If you want, it turns out it's very easy to measure a power spectrum of these velocities in the same way you do for the density power spectrum, and you fit both of them simultaneously. Turns out we published a paper last year that you can actually use the velocities to constrain neutrino masses. The impact on the power spectrum is such that you can detect that potentially. One neat thing we showed this year is that the pure velocities do cross-correlate with CMB lensing, if anyone ever asked. The density field that causes the velocities causes CMB lensing as well. And so the signal is very weak, but is potentially detectable with next generation CMB and pure velocity surveys. And also, it's very important, these pure velocities, for correcting Hubble diagram distances for transients such as supernovae and gravitational waves. And in particular, in a couple of papers in 2020, by myself and others, we showed that the pure velocities are one of the largest contributors to systematic uncertainties in the H0 measurement from the binary neutron star gravitational wave event we detect. In particular, this blue and orange histogram here is the shift that you get if you choose two different choices for that pure velocity. And you can basically say you're intentional or not with the Schutz result, based purely on whether or not you choose a pure velocity from one survey or another. And so hopefully I've convinced you that pure velocity surveys are interesting and worth pursuing. And so I'm going to tell you in the last few minutes how we're going to look at those in the future. And so one of these ways we're going to do this is with the dark energy spectroscopic instruments. So DESI is one of the first stage 4 large-scale structure experiments. We're predicting on the order of 40 million galaxy redshifts between 0 and 3.5. It covers about 14,000 square degrees on the sky and can have up to 5,000 fibers at the same time. There's other people in the audience, along with myself, who can tell you more about this survey if you're interested, because I'm not going to go into too much detail about this, but Hector or Shadab and others definitely be able to tell you some interesting information about that. But one of the things about DESI is that it's so good at getting redshifts that the limiting factor at low redshift for cosmology is not how many redshifts we've got. We basically observe as many redshifts as we would ever need at low redshift. The limiting factor is cosmic variance. So the only way to overcome this is to use techniques such as using pure velocities to provide multiple traces and multiple measurements of the low redshift universe. And so we're also doing a pure velocity survey with DESI. We're targeting elliptical galaxies with fibers to get the fundamental plane measurements. We're also targeting spiral galaxies with 3 fibers to try and measure the rotation curve and getting Tully-Fisher measurements. We published a paper on arXiv this year, which is currently under review, showing that we expect to be able to get 186,000 measurements from DESI alone. So this is, again, a 3 times improvement over the 55,000 that we've managed to obtain so far. This is what that distribution will look like in redshift compared to current data sets. So the constraints I was showing here was basically a combination of green, red, and blue. With this data set here, Tully-Fisher in dashed and fundamental plane in dotted, we'll be able to explore in a much more detailed way the local universe. And our predictions for the growth rate of structure are pretty amazing, if I do say so myself, in particular at low redshift, because we have the cosmic variance limiting what you can get from redshifts only. So for instance, from DESI BGS, if you have a combined survey of DESI bright galaxies and pure velocities, you find that your constraints on the growth rate of structure are basically more powerful than any we've ever obtained before in the local universe. And a factor of several improvement over what each of these probes could do individually. And so public data release for DESI, in particular for the DESI pure velocity catalog, will be available in a few months, hopefully. And we are already working on year 1 data at the minute. But DESI, unfortunately, only covers the northern hemisphere. And so we've also proposed another survey, which is also going to happen, and in which I'm also working, called the Foremost Hemisphere Survey, and that will cover in the south. And so hopefully, by the time we've got DESI and 4HS done, which will be in maybe six years' time, we'll have data which covers both the blue patches, which is DESI, and the entire southern hemisphere with 4HS. The 4HS pure velocity survey is going to observe a similar number of galaxies, But more interestingly, a lot of the local structures that I was talking about for that bulk flow measurement that may be of interest, we may want to cover to try and resolve these tensions, just so happen to be in the southern hemisphere. That includes Shapley, that includes the Vela supercluster. And so this is really perfectly placed to capture some of the most interesting nearby structures. And if we go one step further and say, what would our data sets look like after you've got DESI and 4HS as the current data, this is what we expect. So we expect that at high redshifts, really, we're getting an amazing data set. And so this is guaranteed to happen. We're already planning for this. It's got guaranteed time on foremost, and it starts in 2024. So just to finish up, hopefully I've convinced you that over the next 5 years, the combined redshift and velocity surveys really offer the potential to produce actually the first 1% measurement of the growth rate. So if I run the forecasts for DESI plus 4HS, these are the error bars we get in red. And so this error bar here would, if you combine all three into a single measurement, actually would be the first 1% measurement of the growth rate from a combined DESI and 4HS redshift and velocity surveys. And so I guess the question is, will GR still be correct and work out in a few years? And hopefully we'll know more if you come talk to me. Thanks.
Okay, questions by Nick, maybe? Oh, okay.
Scatter you're getting in the distance estimator?
So the scatter in the fundamental plane is 21%, I think. It's basically proven almost impossible for Tully Fisher or fundamental plane to really reduce that below 20%. The errors, for a long time, the error on the velocity dispersion was the dominant of all the observational errors, and that added a few percent scatter. But we've really reduced that down with SDSS. We'll reduce it down even further with DESI, we think. But 20% really seems like the fundamental flaw due to astrophysical effects. So the only way to overcome that will be adding in more parameters, stellar mass, age, something like that. The problem is those are also very difficult to measure for large.
When the fundamental plane first appeared, there were quite a few papers by Georgofsky and others claiming you could also do what was called the photometric fundamental plane using shape parameters and things. And you have, I imagine you have Cirsic parameters for all of your galaxies. Have you tried to see if that can, you know, in a fourth dimension, you can tighten up the relation?
So we haven't, but there is a student working with Ned Taylor at Swinburne University who has a paper drafted on that. They find that the Cirsic index in particular can improve the scatter slightly, but still not below this 20% sort of floor.
Okay.
Yeah.
Final thing. So what's the sign of the correlation between the surface brightness systematic and the group richness? Are they higher surface brightness in the bigger groups?
Yeah, let me go back to that plot.
You were challenging us to come up with a
yeah.
explanation.
If you
Maybe we should blind it.
If you solve it in the time it took me to give the talk, then that'll be embarrassing. But yeah, so as you go to larger groups, the surface brightness goes down.
Goes down.
Goes down. So if this is the richest group here in this PDF, and this is the groups of only 1 or 2 members over here in the lightest color. So that would be consistent, for instance, if we underestimate the surface brightness of galaxies in groups, because it's just difficult to work out the difference between the galaxy and the background light.
Yeah. Okay, thank you.
Okay, next question.
Yeah, the mocks that you used for the comparison with the bulk flow, are they constrained realizations or just?
No, they're not constrained. So they are just random lambda CDM observers. We produce effectively Kohler mocks for the 3 individual surveys, but in the same box. And then we stack them in the same way we have for the data, which means you can also test if you offset the velocities in one by some value, what effect does that have? And that's what we've done. But they are not constrained realizations. They don't condition on the fact that there could be like Shapley or Vela or Virgo nearby.
But does it make sense to use something like Elucid, which has these constrained realizations now?
Yeah, I mean, so one of the things that we haven't done, but hopefully people are doing or will do, for instance, is you can run constrained realizations and reconstructions on this cosmic flows data, and then measure the bulk flow from that. And it'd be really interesting to see if they also find a large bulk flow there, or if, for instance, the presence of these structures means that you should expect to find a large bulk flow compared to a random lambda CDM observer.
One more final question over there.
You mentioned neutrino mass. What sorts of constraints do you get? And how does it scale with the redshifts that you can go out to?
Yes, so the neutrino mass constraints that I mentioned somewhere here, they the velocities add some information, not an overwhelming amount, compared to if you take Planck past the entire redshift range of DESI, the impact of the pure velocities is pretty minimal.
And that's because of the redshift coverage?
And that's because DESI, if you count and cover the full redshift range, is just a huge amount of data, most of which is, covers an enormous cosmological volume, and ultimately volume wins in terms of measuring cosmology. You get more modes, you get more information. But what we did find interesting is if you get rid of Planck and you say, let's try and make a neutrino mass measurement where we have only early universe and we have only DESI, pure velocities really, really help there.
Yeah.
So if you had DESI, BGS, main survey, and pure velocities, you could produce a constraint on neutrino mass, which is comparable to what we currently have, but it would not be competitive to what we'll have with DESI plus Planck in the future.
Makes sense. Yeah. Thanks.
Okay, thank you very much. Let's thank the speaker again.